Hi again. This video is on conservation of momentum, and it is the last of the 4 videos that make up our conservation of energy and momentum unit. So the essential question that we are trying to answer in this video is, how can conservation of momentum help us explain and predict the motion of colliding and exploding objects? So the big idea here is that momentum is conserved in closed systems. We've talked about closed systems many times in this class in terms of mass and energy, and now we're applying it to momentum. So the total momentum in a closed system is always a constant. If we can separate those objects from the rest of the world, the momentum of those objects are going to stay a constant. This also means that if you add up all the momenta of objects in a closed system at one moment in time, it's going to be equal to the momenta of the same objects later. So nothing is lost from the system as time goes on. The individual momentum of an object may change inside the system, but the total momentum of the system does not. Some common scenarios where we can observe conservation of momentum are in collisions and explosions. These can be in grand form, like if you had 2 asteroids colliding together, or they can be simple things from your daily life, because collisions and explosions just refer to the direction that these objects are heading in. So, for example, as you walk, you push off from the ground and your foot and ground move apart. It's like a little mini explosion in terms of direction. So when objects collide or explode, their velocity is changing either in size, so magnitude, or in direction, or in both. So an object can be moving at a positive velocity. When it hits something, it can bounce and go back with a negative velocity, and that's essentially an explosion. Since our equation for momentum says that momentum equals mass times the velocity, if you change your velocity, including the direction, then your momentum is going to change as well. So when you look at this equation here, you can see that there's a linear relationship between velocity and momentum, and mass is conserved. But the other thing about the law of conservation of momentum is that it means for every object that gains momentum, another object in that system must lose an equal amount of momentum. And we're going to show you what we mean by looking at a few examples. So let's look at a simple explosion example and see if we can predict what's going to happen in this scenario. So we have 2 ice skaters with equal masses, and they're going to push off from each other, sending each other in opposite directions. So if we think about their velocities, they're going to have the same magnitude for their velocities, but one is going to be moving in a positive direction and the other is going to be moving in a negative direction. So let's investigate why this is. So let's investigate what's going on with this problem. So in a closed system, which is indicated by that solid line, momentum is conserved from one moment of time to another, just like mass is. So I would start this problem by drawing a box around the initial position of those 2 skaters and showing later in time the same skaters in the same box but spread apart because they've moved apart. So let's look inside that first box at the individual objects. When they first started, they each had no momentum. And we know this because they were not moving. They each had mass, but mass times a 0 velocity is going to give you no momentum. So their total momentum must have been 0 before the explosion. And since momentum is conserved in a closed system, this means that every moment in time after the explosion, that the momentum is also going to equal 0. So we know over here in our picture of the skaters after the explosion that their total momentum must equal 0 as well. Why does this make sense, you might ask? Because we know that those skaters are moving at this point. We know that one skater has a positive momentum and the other skater has a negative momentum because one has a positive velocity and the other has a negative velocity. But because their masses are the same, those momentums are going to cancel out to also equal 0 because in this system, momentum is conserved. So the momentum of individual objects in a system can change, but their total has to add up to the same as what it was before. So here's a slightly more challenging problem. Let's look at what's going to happen when a big football player pushes off from a little girl. You can see in this problem they're both still on ice skates, and we're doing this to minimize friction, to simplify things. But I want you to think about what should happen in this scenario. So hopefully you'd recognize that if these two push off from each other, the little girl is going to move forward with a large positive velocity. The football player is going to move backwards with a smaller velocity in the negative direction. So let's look at this in terms of systems to see why this makes sense in terms of conservation of momentum. Although the objects in the system may have different velocities, so the football player is moving at a small velocity compared to the little girl, and velocity is not conserved, they have equal but opposite momenta because the momenta are conserved. So in the beginning, we have a football player with a large mass times a 0 velocity, and a little girl with a small mass times a 0 velocity. So our total momentum for the system is 0. If you have no velocity, you can't have any momentum. Because these two are in a closed system, at a later point in time, their total momentum should be the same. It should also be 0. So why does this make sense? Well, our football player has a large mass and a small velocity headed in the negative direction, and our little girl has a small mass and a large velocity headed in the positive direction. So when you add up their individual momenta, they will cancel out, and your total of the system will still be 0. We're going to be doing some problems solving for momentum mathematically in class. But before that, I want to introduce a tool for tracking momentum called an MVP chart. So the two previous problems we've done in this video have involved explosions. This problem is going to be looking at a collision. So let's look at the collision between a Mars-sized planet and Earth. This is actually one of the ways that scientists believe that the moon was actually formed, was from a really large object striking Earth and knocking a chunk of it off right when the Earth was forming, which is why the ages of the moon rocks are the same as the ages of the rocks we have on Earth. So in our before scenario, we have a Mars-sized planet hitting Earth or right before they collide. So the instant before this planet collides with Earth. And then the after scenario, we have the big mass of things mushed together. You can see that the variables we're looking at in this chart are mass, velocity, and momentum, and those form the rows. And the columns have titles at the top indicating Mars and Earth in the before picture, and then in our after we have one blob that we're going to call Mars Earth. So our chart shows what's going on in the system right before collision and then right after collision. We're going to do an example of this problem in class, but essentially you go through and you fill out the boxes that make up this table. The two rules that we need to follow when we're filling out these boxes are that mass is conserved and that momentum is conserved. So the total mass of the system cannot change from before to after, and the total momentum of the system cannot change from before to after. Another key thing to note is that velocity is not conserved. So the total velocity of these objects does not have to stay the same from before to after, just mass and momentum. So why isn't velocity conserved? Well, objects can change velocity during a collision or explosion. This can be in the direction that they're traveling, or it can be in the magnitude of the speed that they're traveling. We also know that smaller objects must change velocity more than bigger objects during one of these collisions or explosions. And the example that we looked at was the one with the football player pushing off against a little girl. She's going to move a whole lot more because she has a much smaller mass than a big football player who has a larger mass. So if you think about a bug flying at negative 60 meters per second directly at a bus that's coming the opposite direction at 60 meters per second, the bug is not going to cause that bus to stop. The bus's velocity is barely going to change at all because it's a very large object, but the bug's velocity will change dramatically going the other way. So velocity is definitely not conserved. Another thing to note is that mass has an inverse relationship with the change in velocity in a collision or explosion. So the larger the mass an object has, the smaller the change in velocity it's going to have. So to summarize, think about how we can use conservation of momentum to help us explain and predict the motion of colliding and exploding objects. So we're looking at objects' mass and their velocity to figure out what's going on with their momentum and what they should be doing after impact. Please take this time to fill out the graphic organizer at the end of your notes and to write a short summary of what we covered in this video.